The one that I'm reasonably sure we would need some help with is this one, or you would need some help with is this one. And maybe some of you have some ideas as to how to do it already. And I'm welcome, you're welcome to share those ideas with the class. But what I tried to do was to give you an idea of what is actually going on here. So we have a point, and let's say this point here is 2, 7. Not exactly 2, 7, but I'm just saying, it's somewhere up here. I'm just going to label that 2, 7. All right, minus 2, 7. And there's a function. It's a function that's turned down, a quadratic function that's turned down, minus 2x squared plus 6x minus 5. And what's happening is that it creates a tangent from that point to 2 points that are on the curve. There's a tangent line from that point leading up to that 2, 7. So both lines connect at 2, 7, and both lines touch the curve at those 2 tangents, right? So what is minus 2? Okay, thank you, Ashwan. Yeah, thanks. It was minus 2. You're absolutely correct. So how do we do this exactly? Well, I'll show you how I thought would be a good way for us to deal with this. First of all, I want you to think back to first principles. When we were doing first principles a while back, before we got to the shortcuts, I said to you, there may be a good reason why we're looking at the first principles method for doing this. One of the approaches to first principles, if you remember, was where we took the f of x minus the f of a and, excuse me, and then we looked at the limit as x approaches f of as that thing got smaller and smaller, right? I hopefully you remember that way of doing the derivative. So what if we were to attempt to use this approach, right? What if we were to attempt to use this approach, bringing in that minus 2, 7? Well, that would mean that I would have the function, which is f of x, which is this thing here, as my f of x. I'm going to write that down as my f of x, the minus 2x squared plus 6x minus 5. And I'm, again, trying to use this point of minus 2, 7. So I'm going to minus from that the y value at this point, which is the 7. I'm going to put that over x minus the x value, which is minus 2. So x minus minus 2, and we're just going to put x plus 2 for that, right? Because that's the way we find the slope of the function. Now, I'm going to set that equal to, so we know that this would find the slope of this function at 2, 7. Let's just be clear on that, right? At 2, 7, minus 2, 7, I keep saying 2, 7. At minus 2, 7, we would be able to find the slope of this function by plugging in that information into this version of first principles, right? F of x, which is the function, f of x is minus 2x squared plus 6x minus 5. The y value at that point, f of a, is 7, so we're minusing 7 from that. We're putting that over the x minus the x value at that point, which is minus 2. So we put x minus minus 2, or x plus 2. Now, that would be the slope of this line that we're trying to find, right? Because remember, at 2, 7, that this is going to have some slope that's connecting with the function. All right. But we also have, we can set that equal to something else that should represent the slope of this line that we're talking about, right? How else can we find the slope of a line apart from using this first principles method? What other tool do we have for finding the slope of a point on the line minus 2x squared plus 6x minus 5? Right? What other tool do we have for that? The derivative. And we have a short version or a shortcut to find that derivative. So why don't we set this thing that we just got, which would be the slope of this line that we're trying to find, and set that equal to the derivative of this function using the shortcut method, which is, as you know, minus, what is that, 4x plus 6. Right? Both of these things are slope calculating tools. One is a first principles tool, and the other one is the shortcut that we developed from the first principles. So if I took the dy dx of this, right, I'm taking the dy dx of the minus 2x squared plus 6x. As you all know, that would be minus 4x plus 6, right? And I'm also setting that equal to, because they should have the same slope, right? They should have the same slope. It's the same tool that we're using. One is a shortcut method. The other one is the first principles method. Those two things should be equal when we're dealing with minus 2, 7. So what I'm going to do now is I'm going to solve for x, because this looks like something that has only one variable, and that variable is x. So let's see if we can do this. I'm going to cross multiply to do this. Put this over 1. I'm going to take the bottom of this side and multiply it by the top of this side, right? So I'm going to take minus 2x squared plus 6x minus, I guess, 12, and set that equal to minus 4x plus 6 multiplied by, let me just erase this right here, sorry, multiplied by x plus 2. All right, let me do a quick check-in. Did I kind of leave anybody too far behind there? Anika, how about you? Do you feel that that step made sense to you, what I just did? Anika, what do you think? You're good. Okay. So we took the first principles approach, and we're saying that at 2 minus, I keep saying 2, at minus 2, 7, right? I would put the minus 7, or actually the 7 here, I minus it from the top, and I'd put the minus 2 at the bottom, and that's what it would look like. But then I can set that equal to the thing that we also know finds the slope, which is the minus 4x plus 6. That's the derivative of the minus 2x squared plus 6x. I know we're just trying to solve for x. Let's see if we can take this further. So minus 2x squared plus 6x minus 12. And we can FOIL this out, right? We can, go through the process of multiplying this out using FOIL. So minus 4x times x is minus 4x squared. Minus 4x times 2 is minus 8x plus 6x plus 12. Okay, so all I've done so far, can I go over it? I sure can. I sure can. No problem, Ariane. I just saw your message. Remember, Ariana, when we started looking at the first principles method of finding derivatives, do you remember this function at all? Do you remember this format at all? F of x minus f of a over x minus a? Do you remember? Oh, you got it now. Oh, okay, good. Okay, perfect. So now I'm just multiplying this out. And obviously what I'm looking at here is a quadratic. And I'm trying to solve for x. I'm going to bring everything over onto one side. I'm going to bring that minus 4x squared over to the left. So that's going to be 2x squared, positive 2x squared, the minus 2x squared plus the 4x squared. I have a minus 8x and a plus 6x, so that's minus 2. I'm going to add that to this side, so that's a plus 8x. Excuse me. I just want to make sure everybody's following here. Minus 8 plus 6 is minus 2, so that's going to be a plus 2 on the other side, so that will be 6 plus 2, which is 8. And then the minus 12 and the plus 12 is going to give me minus 24 equals 0. Okay, so I'm thinking, okay, looks like I'm going to get two answers, but that makes sense because, okay, I've lost my graph. It sort of ended up, getting, well, I can put it back actually. I can put it back. I would think that there would be probably 2 points that would connect with the 2 minus 2, 7. One would be maybe about here, the other one would be somewhere down here, and that's just going to graze the graph somewhere. Okay, so that the two solution that we seem to be getting looks like it's going to make sense. Okay, how do I solve this? Right? What's the next step in solving this? Help me out, folks. Give me some clues here. 2x squared plus 8x minus 24. What do I do now? Factor. Absolutely. But what am I going to factor? I'm going to factor out 2 first, because that's a common factor. All right, if there's a common factor, even if it's quadratic, I'd factor that out first. So x squared plus 4x minus 12 equals 0. Okay, and now I can factor again. So 2 into, let's just think for a second. Looks like 6 and 2. So x plus 6, x minus 2 is equal to 0. Now, that means that I think I found the two x values that are the connecting points up here, right? One x value is probably over here somewhere. There's another x and y value somewhere down here. And I think I found those two x values. So x equals minus 6 and 2. And I can easily find my y values for each of those. That's not hard, right? Now, what I'm going to do is I'm going to see if I can challenge you to finish this question on your own. First of all, I can find my y values by taking each of these values and putting them back into this function. So that's not hard, right? I can find my, so wherever this function was at 2, so there's 1 at 2, 1 at minus 6, approximately, right? So those are your two x values, 1 at 2, 1 at minus 6. I'm going to say, I need to figure out, I'm just going to do one of them. Y equals, I'll do the one with the 2. So that's a nice positive number to work with. So it's minus 2x squared plus 6x minus 5. So minus 2 times 2 squared plus 6 times 2 minus 5. All right, let me just double check that. Double check. Minus 2 plus 6 minus 5. Okay. Okay, right. So that gives us minus 8 plus 12 minus 5. Let me double check that. You know, I make mistakes sometimes. 4, so 2 minus 8, and 6 is 12. Okay, so minus 13 plus 12 should be minus 1. All right, that's what I'm getting. So that would be 4, minus 1. So I have 1 point at 2 minus 1. So my graph isn't really that accurate because I have it looks like it's something. I wasn't really trying to correctly draw 2x squared minus 2x squared plus 6x minus 5. I was just drawing an arbitrary upside down function. But one of the points of contact is 2 minus 1. So all I need to do now is find a slope between this point here, the minus 2, 1, right? I can actually get the slope by putting it into this, by the way. So into my slope calculation right here. I can get that slope right there. And then I can just easily find my y equals mx plus b because I was asked to find the equations of the lines. So the slope is easy enough for me to find by using the derivative, minus 4x plus 6, or I have 2 points here, right? I can easily figure out what the slope is between those 2 points. And I can do the same thing again now with the minus 6, right? Find that other point and find the equation of that line. And can I leave that there? Or do people feel comfortable enough with what I just did to finish that question? That's what I need to find out. Braden, what do you think? Do you think you could finish that question on your own? You think that is enough for you, Braden? Where's Braden at? Where's Braden? Hello, Braden. What happened to Braden? Okay, Braden. I'm asking a question. Do you think that what I've done so far is enough for you to figure out the question? Hopefully you've been paying attention, hopefully. And what I've done so far is enough to get you to finish the question so I don't have to spend any more time on it. Is that good enough for you? Just asking generally. Braden, what do you think? Or do we have to do more? You think so? Okay. Carly, how about you? Do you think that's enough for you for that question? All right, just generally, you know, if you think we need to do more, you need to let me know. Carly, what do you say? You're okay with that so far? Okay, all right, let me move on then. So that was number 4. That was one of those questions that I thought, you know, people legitimately would have, would need some help with. So hopefully that makes sense. Okay, let's tackle this one. This graph has a horizontal tangent at -1, -6. Find A and B, and then determine the coordinates of the other horizontal tangent. So it looks like we have two horizontal tangents on this rational function. But guess what? We didn't get the rational function. We only got that we have a quadratic on top and we have a linear on the bottom. So the top of the function is ax squared plus bx plus 35. We don't know the a, we don't know the b. And then the bottom of the function is x minus 5. Wow. What are we supposed to do with that? Well, what do you think is a good way for us to get started on this? Right? We have two unknowns here. And we only have one point that we know is on the function at -1, -6. Right? We have an a and a b, and we don't know either one. But we know there's a horizontal tangent at -1, -6. So what do you think? I'm looking for ideas. I remember, these are questions that plug in the point and substitute. Absolutely, Adam. That's the first thing we should be doing. We should be plugging in at least we know this point is on the line, right? Horizontal tangent is at -1, -6. So -1, -6 is on the line. We can certainly start. We don't need any calculus for that. We can certainly start by building the relationship between A and B by plugging in that -1 and that -6. That's exactly what I'm going to do. So -6 is equal to, so if it's -1, it's going to be A, because -1 squared is still 1. And then I'm going to have -1 times B, so that's going to be minus B. And then plus 35 divided by -1 minus 5 is -6. Okay, so I'm just plugging in all the stuff that I know at this point. So if I just gave this to you, where would you go next? Not just Adam, but everybody else. Right? Can I simplify this sum? Right? Think about what I did a few minutes ago when I had some rational, there was a numerator denominator kind of thing. What do I do with that? Come on, folks. I'm expecting you to jump in and give me some ideas. How do I move forward to simplify this some more? I can't solve for A or B yet because it's two unknowns, but I can at least make it look a little nicer. How? Multiply the -6. Of course, Ashwan. Thank you very much. So that's going to be 36 is equal to A minus B plus 35, which means that A minus B is equal to 1, taking that 35 from the other side. Okay. Hopefully everybody followed the multiplying by the -6 on the other side. It's really cross multiplication is what we're doing. And now we know that A minus B is equal to 1. Okay, so that has nothing to do with calculus. Nothing whatsoever to do with calculus. But we were told that at -1, -6, we have a horizontal tangent. How does that help us? Horizontal tangent means what again? Remind me what a horizontal tangent means to you, right? What's going on? Slope, thank you, Adam. Slope is 0. Well done. You say it's a kind of yes, I'm going to say it is a vertex. Just so you know, this is not a quadratic. So when you say vertex, it does turn at that point. But yes, it has a horizontal slope, which is a slope of 0. Perfect. Yes, Stephen. Local max or min. I'm going to say absolutely right on that, right? Local max or min. A horizontal tangent. Well, there's one other possibility, I should say. You could actually, I'm glad you brought that up, Stephen, because you could have a horizontal tangent. I'll just put this on the side here, and I use a different color for this. You could have a horizontal tangent if you have like a cubic function that looks like that. There's actually a horizontal tangent somewhere around. Where is my thing that I can use to, oh, here it is. You would have a horizontal tangent somewhere around here. All right, just so you know. And that's not really a local max or a min. And we're going to get some more into that later on. But you do have a horizontal tangent on a curve where it looks like it's called a point of inflection, but we'll get some more into that. It looks like it's about to turn down and it sort of turns and goes back up again. So you would have a 0 horizontal tangent right there as well. Just FYI. And I thought I just mentioned that since it came up. All right, so I'm going to erase this. All right, let me come back to over here now. So A minus B is equal to 1. And we also know that there's a horizontal tangent, and you've already told me Adam and everybody else, and Stephen jumped in as well and pointed out that that means that you have a slope of 0 at that point. How does that help me out? What do I do with that information? Right? What do we do with that information? Where do we go with that? Folks, I do need some participation here, because these are questions that I would expect that you would be able to think through and come up with some ideas, even though you may not necessarily be able to do everything on your own, but at least you have some ideas as to where to go. What do I do with information that says that there's a horizontal tangent at -1, -6? Where do I go with that? What do I do with that? And yes, Adam says that the slope is equal to 0 at that point. So how can I put that information to good use? Make it, okay, what are we making equal to 0? You mean the function as it is, f of x? Do we put the f of x function equal to 0, Sarah? The derivative. Thank you very much. So we have to find the derivative function. So let's do that. I still have the dotted line here. Let me get rid of that. And let me actually go back to black as well. Okay, so we're about to find f prime of x. And that, as Sarah just said, is what we're going to set equal to 0. So f prime of x. Now, obviously, or hopefully it's obvious, we should be looking for the quotient law on this one, right? Quotient law says that we're going to take the derivative of the top, which is, well, here's our function over here. I'm going to take the derivative of the top, which even though we don't have the a and the b, is going to be 2ax plus b. Actually, you know what? I might not have enough room here. Times x minus 5 right? Minus, and I'm going to derive the bottom, which is just going to be 1, and multiply that by the top, which is going to give me the ax squared plus bx plus 35. Oh, I'm trying to scroll over here. Oh, that didn't work. I'm just trying to scroll to my right here. It's not doing it very well. Okay, minus ax squared plus bx plus 35. And all of this is over the denominator of x minus 5 squared. Okay? All right, let's see what we can do with this now. I'm going to go ahead and, first of all, erase this. And let me just check in with the room here. Does that step make sense so far? Fernando, how about that step? That looks okay to you? That finding that derivative using the, okay, great. All right, so what I'm gonna do now is I'm gonna multiply this all out and collect my like terms, see what we got here. So that's all equal to, so 2ax times x is gonna be 2ax squared minus 10ax plus bx, I'm going to run out of room again, minus 5b minus ax squared minus bx minus 35. And I'm just going to double check that, make sure that I'm good. And on the bottom, we still have x minus 5 squared. Okay, I'm just going to double check the top here. 2ax times x is 2ax squared, 2ax times minus 5 minus 10ax plus bx minus 5b minus, okay, what did I do wrong now? We said on the numerator after the minus sign there was a 1. Where's the 1 from? Okay, let me just make sure now. Okay. Oh, so you're okay now? Okay, no problem. All right. Okay, so let me see what I can do here now. So I have a 2ax squared, and I also have an ax squared here. So I'm left with 1ax squared. Right? I'm just eliminating stuff as we go along. I'm going to take that out and take that out. I have a minus 10ax. Well, that's still there. So minus 10 ax. And then I have a minus bx and a plus bx. I'm going to take those out. I have a minus 5b. And then I have a minus 35. All over x minus 5 squared. I know it's a kind of a long question, but that's the way that goes. Okay, excuse me. So here's what we have. Ax squared minus 10ax minus 5b minus 35. And this is roughly what the derivative is. Now, let me take you back, if I can, to something else that we'd worked out before, that a minus b is equal to 1. Or, of course, we can say that a is equal to 1 plus b. That's something else that we can certainly derive from that, right? That's a given. We also have all of this over here, ax squared minus 10ax minus 5b minus 35. So where do you think I need to go next? Now remember that we're saying that this thing here is going to be equal to, let me just take you back to the original question. Okay, so ax squared minus 10ax minus 5b minus 35 all over x minus 5 squared. We also know that a is equal to 1 plus b. That's something else that we know. And we also know that when you plug in the minus 1 into this, we should get 0, right? I mean, that's what we're saying. This is the derivative of the function. And we're saying putting in that value of minus 1 that Adam just gave us as the coordinate, that should give us 0. So what do you think I need to do next with this then? All right? What do you think I need to do next with this? Anybody? I'm reminding you, one more thing here. That a is equal to 1 plus b. So what do you think, folks? A is equal to 1 plus b. So substitute that in. Okay, so we can do that as well. So 1 plus b, x squared, plus 10 times a. Sorry, 1 plus b. And the other thing that we should be doing, in fact, let me back up a little bit here. We should also be putting in the minus 1 into the function at the same time. Let's just cut to the chase here. Oh, sorry, hold on. Okay, so we should also be putting in that x equals minus 1 into the function as well. So it's 1 plus b for the a, and minus 1 squared, because we're putting in minus 1, minus 10 times the 1 plus b again, times the 1, minus 5b, minus 35 is equal to, and over x minus 5, by the way, so 1 minus 5, I guess, is equal to 0. So it's minus 1 is squared. Yeah, you're right. You're absolutely right. Thank you. Okay, so let's see what we got here now. Okay, now let me point something out to you. When you have a rational function like this, it doesn't seriously matter what's on the bottom of the function. If it's set equal to 0 and you're trying to solve for something, you really should be figuring. Thank you, Sarah. You really should be figuring out the top. If you cross multiply right now, it's really the top that matters. So this is equal to 1 plus b, right? And minus 10 times all of that. So remember, it's minus 10 times, and there's a 1 here, so that doesn't really matter. So minus 10 minus 10b minus 5b minus 35 is equal to 0. And I'm pointing out that what's on the bottom of this, I'll put it in anyway, the 1 minus the 5 squared. Doesn't seriously matter what's down there. All right, because really when you set something equal to 0, it's the top that really makes a difference. It's really the top that is the thing you want to focus on. So is it minus 10 times 1 or minus 1? Minus 1, minus 1. Where's, oh, was this supposed to be, let's see. Well, x is minus 1. You're quite right. Thank you very much. So this actually should be plus 10 then. Thank you. You caught me on that one, Adam. You're quite right. I should have been a minus 1 for the x. So let me double check all of this now. So that should be 1 plus b times this minus 1 squared. And then it's minus 10 times 1 plus b times 1. And that 1 should be a minus 1. So let me just change that. And that changes this to plus 10. Then the minus 5b minus 35. Okay. All right. Let's see if we can collect all of our stuff together now. So that should be equal to 11 minus 35 should be minus 24. All right, and then the b's, let's just think now, that's 11b minus 5b should be what? 6b plus 6b is equal to 0. I'm just going to quickly double check that. So that's 11 minus, so 11, so that's minus, yeah, minus 24. Yeah, okay, good. And then the b's, that's 11, yeah, 11 and minus 5 is 6b. Okay, so, and again, I'm not focusing so much on the numerator, on the denominator, because that denominator really doesn't matter. It's the numerator that matters. So therefore, 6b is equal to 24. So our b is 4. So I'm going to leave this one at this point because getting the b should easily give us what the a is over here. Where is it again? We should be able to get the a very easily from that. And we should be able to finish the question at that point. Okay. It does ask us to get the A and the B, and that should be fairly easy from that point onward. Okay, so I'm actually going to move on from there. And again, if anybody wants to come back and ask me anything else about that, we can certainly do that. Are we fairly comfortable with that now? We get on to number 8. Okay. It tells us that the derivative of the function is 6x squared plus 6x. So we didn't start off with the function, we started off with its derivative. Then it says find the function itself if the function value at 1 is equal to 10. So is there some way we can kind of go back to where the actual function is, right? If they give us a derivative, can we take it and go backward? No, even though this calculus course doesn't involve something called integration, it only does differentiation or derivatives. There's a whole branch of calculus called integrals. And in a sense, that's what we're going to be doing now. An integral is a reverse of a derivative. And we're going to take this function, which is a derivative function, and try to go backwards to what was the original function. Now, let me remind you how this works. If the function is equal to a to the power of n, then what we do is we take n and multiply it by a to the power of n minus 1. Right? That's how we normally, for simple polynomials, that's how we normally find a derivative. Right? That's a shortcut method for polynomials. Well, what if we were to reverse that and go the opposite way? In other words, rather than multiplying by the n and then minusing 1, what if we added on 1 and then divided by the number in the front, which is the exact opposite of what differentiation would do? Okay, so in the case of, let's try this out. So in the case of, this is 6x squared plus 6x. So the prime is 6x squared plus 6x. So what I'm going to do is, I'm going to say this. This is the f of x itself, the original function. Add 1 to the 2, So add 1 to this first, and then divide it by the number in the front. So if I add 1 to the 2, I'm going to get 3, and then I'm going to divide 6 by 3, which gives us 2. So it's 2x cubed. Let's do the same thing here. Add 1 to the 1, there's a 1 there now, and divide this function, this coefficient by that number, which is going to be divided by 2 in other words. So that should be 3x squared. All right? Now, if you go ahead and in your mind differentiate the 2x cubed and the 3x squared, you can confirm that you're going to get back the 6x and the 6x squared. Right? Right? Which is what we would expect it to do. But I'm going to do one more thing. When we do integration, we talk about what I call definite integrals and indefinite integrals. We're going to refer to this as an indefinite integral because this could have had a constant which we don't know, and I'm going to call this constant just c. Because if there was a constant, I think you'd agree with me, that constant would have disappeared. It would have gone to 0 if I had differentiated the original function. So if I took the dy dx of this function now, I would still get the 6x squared plus 6x, and that c would have gone to 0. So let's put that c in because we really don't know if there was a constant or not. So now we have something that we can actually put this into. This f of 1 equals 10 into. So I'm going to put the 10 and the 1. So that means that 10 is equal to the 2 times, sorry, what was it again? 1. 2 times 1 cubed plus 3 times 1 squared plus c. So now we have a way that we can get the c, the missing c. That's the part that we could not get by just simply using the integration method of adding 1 and then dividing by that number in the front. Right? So I'm just plugging in 1 and setting it equal to 10 because f of 1 is equal to 10. Okay, so 10 is equal to 2 plus 3. 1 cubed times 2 is 2. 1 squared times 3 is 3 plus c. So c is equal to 5. 10 minus 5. So I now have the function, right? The question asked me, find the function. Well, I now have the function, right? The function, the original function, f of x, is the 2x cubed plus 3x squared plus 5. Right? Here's the function with the c that we didn't know. We had 1 point, the 1 and the 10, plug that in, and we found out that c was equal to 5. Here's your function, right? And in this function, plug in 1, you're going to get 10. The derivative of this function is 6x squared plus 6x, which is exactly what we said the derivative was. Okay? So that's not so hard at all. Jessica, does that kind of sit okay with you? Does that sound about right to you? Am I leaving you behind or anybody behind on that one? Jessica, what do you say to that? You're good. Okay. All right. So remember, any of these questions, so what's going to happen on Tuesday, let me just sort of give you a little heads up on that. On Tuesday, I'm going to give you, the whole period is going to be an evaluation, right? The first part is going to be like a test, and that's probably just going to be mostly multiple choice, if not all multiple choice. You don't have to give me any, steps for that because multiple choice anyway is just you get it right or wrong by picking the right answer. Then the second part is going to be the assignment part, which is going to involve questions like what we're doing right now. And yes, I will need to have your steps on that. And what I'll probably do is set up a separate place for you to upload your answers and give you more time to do that. Because I'm going to give you a limited amount of time to put your answers in, but give you more time to upload your documents because I know that some of you may have slower connections to work with, so it might take a while for you to upload. So I'm just letting you know what the format of the test might look like on Tuesday. So there you go, folks. That was number 6. Let's move on. Number 7, determine the value of k such that the g of 1 is equal to 5 if g of x is equal to, and they give you x plus k over x squared minus 2. Write the equation of the tangent to g of x when x is equal to 2. Write your answer in the form of y equals mx plus b. Okay. So when you put 1 into the derivative, you get 5. and they give you what the original function is. So I think immediately we know that we're going to have to find the derivative of this function, right? Even though we don't know what k is, we can find the derivative of the function even though we don't have the k. So let's go ahead and find that derivative. So the g prime of x, and I would think that using the quotient rule would be the best way to go about this. So I'm thinking derive the top, which is just simply 1, times the derivative of the bottom, so it's 1 times x squared minus 2, right? Minus the derivative of the bottom, which is the 2x, multiplied by the x plus k. All of that over x squared minus 2 squared. Okay, let me go over that again. The root of the top, which is 1, multiplied by the underived bottom, so x squared minus 2 doesn't affect it because you're multiplying by 1, minus the root of the bottom, which is 2x, multiplied by the underived top, which involves that x plus k. All of that over the denominator squared. Okay, let's see what we can do with this some more. So x squared minus 2 minus 2x squared minus 2xk. Okay, I'm just multiplying that minus 2x by both of these two terms and putting that over x squared minus 2 squared. Okay, now let's see if we can tidy up the top a little bit. I would have x squared minus 2x squared, which is minus x squared. We still have the minus 2. We still have the minus 2xk all over x squared minus 2 all squared. So even though we don't have the k, we have what would represent the derivative with the k in it. And what else they told us is that if I put 1 into this derivative, I should get 5. That should be enough to figure out what k is. So set this equal to 5, and then put minus, is it 1? I think it was 1, yeah. 1 squared minus 2 times, sorry, minus 2 minus 2 times 1 k, or just simply minus 2k, all over 1 squared minus 2 squared. All right, and I'm quite happy to change anything that I wrote down that is wrong. I mean, that's something that I know some of you are really, really very good at. You're following along and you're making sure that every step makes sense. So that's fine with me. Okay, so let's keep going. So that's equal to minus 1 minus 2 minus 2k, essentially over 1. 1 minus 2, 1 squared minus 2 is just 1, and then you square it, you get 1, is equal to 5. Well, we've seen this before where we just had to cross multiply. Okay, so that means that minus 1 minus 2k, sorry, actually, that's just minus 1 minus 2, that's minus 3. So 5 is equal to minus 3 minus 2k. Okay, so therefore minus 2k is equal to 8, and therefore k equals minus 4. Okay, so that's the first part of the question, unless I made a mistake, minus 2. Yeah, I think we're good. So k is equal to minus 4. All right, now, what else did they ask us for? So we did that. Write the equation of the tangent to g of x when x is equal to 2. Write your answer in the form y equals mx plus b. I don't think I should need to go any further with that, because this is a typical kind of question where you can now write the equation. The equation is now x minus 4. So here's your equation. Here's the original equation. Y equals x minus 4, right? We had that k is minus 4, so we can put x minus 4 over x squared minus 2. So if they ask you now to come up with the equation of the tangent when x is equal to 2. All you need to do is to find the derivative of this function, plug 2 into it, get your slope, write your equation of your tangent. Okay? So again, it's another question that I think I can sort of leave with you, I hope. Richard, how do you feel about that? You think you could finish up that question if you had to, or do we need to do a little bit more than that? Richard, how do you feel about that question? You think you're okay with that? Okay, good. All right, so I'm going to move on. Again, I'm trying to get as much of this done as possible. All right. The normal to this function at 2, 1 intersects the graph at another point. What are the coordinates of the other point? All right, let's see if we can get through this one. Remember what a normal is. A normal is something which is at right angles to some other line. So we always have to find that negative reciprocal when you're trying to find the slope of that other line. So let's see what we can do here. We first of all need to figure out what the slope of the function is on this line at 2, 1, right? So we need to find the derivative of the f of x function. So f prime of x. Now, for me, before I even do this, right, I've been saying to you, I'm just going to erase this for a second here. I've been saying to you that sometimes it's easier, rather than using the what we call the quotient rule, is sometimes I find it easier if you can rewrite the function to use another way to do it. So if I just wrote this function as this, would that make sense to everybody? Is that the same thing as the original function? The original function is 1 over x minus 1. Well, can I write that as x minus 1 to the minus 1? Yeah, absolutely. Thank you. Thank you, Ariana. Everybody else agrees with that? Does that make sense to everybody else, that I can rewrite it that way? Great. So in that case, for me, it's much easier to derive that and quicker. So my dy dx now, or f to the minus 1, is equal to minus 1 over x minus 1 squared, right? So it's minus 1 in the front, and then you're going to be raising this to the power of minus 2. So put the minus 1 on top, and then put the x minus 2 to the power of 2 on the bottom. Okay? I hope you are getting much more comfortable doing these derivatives as we move along with this. All right? So there's my derivative, right? They didn't really need to use a quotient law. Okay. And by the way, just so you know, I should have multiplied it by the root of the inside, but the root of the inside is 1, so it really doesn't change the function. The function is still the same. This had been 2x minus 1. I'd have to multiply by 2 at the end. But this is just x minus 1, so the root of the inside is just 1, so just so that we're clear on that. So there's my derivative. And the question says at the normal. So the next thing I need to figure out now is what is the slope of the function at 2? So I'm going to plug 2 into this derivative. F prime of 2 is equal to the minus 1 over 2. Oh, sorry, that little part there is wrong. So 2 minus 1 squared, which of course is equal to minus 1 over 1, excuse me, which is minus 1. So we now need to find so that's the slope of the line at the 2, 1, right? At the 2, 1, the slope is minus 1. So what would be the slope of the normal is my question. I'm going to throw that out to the class. Folks, what's the slope of the normal? Slope of the normal would be equal to, you're not quite right. You're not quite, okay, no, Stephen is now right, right? Don't forget, you have to do two things. You have to flip it over and change the sign. So the slope of the normal, the negative reciprocal, is actually 1. Okay? Everybody follow that 1. Not 1 over 2, Taj, but 1. Remember, you take the number that you have, the slope you have now, you flip it over, change the sign. So if you flip over minus 1, you're still going to get minus 1, but then you have to change the sign, and it gives you 1. Taj, it makes sense. Just want to make sure that Taj is clear on that and everybody else. Sarah was okay before. Adam, you see why it's 1, not -1. All right. Okay, good. All right, good, good, good. So slope of the normal is 1. So that's important for us to know. And we're trying to find the normal means. And by the way, we can actually find the equation of this line now, right? I know we haven't actually done that for any of these questions that we've been doing here, but let's just do that now. Let's find the equation of this normal, because we actually do need the equation of this line. So we know that this has a slope of 1, and it goes through the point 2, 1, so that's not hard. So remember, y equals mx plus b, right? And we have the point 2, 1, so I'm going to put 1 here is equal to the slope of 1 times 2 plus b, right? The point is the point 2, 1. Did I do that right? Yeah, 2, 1. So 1 is the y and 2 is the x. Yeah, 1 is y, 2 is the x. With a slope of 1, which means that b is equal to -1. So my equation is this. Y for the normal, this is the equation of the normal now, is equal to x minus 1. So we have the equation of this normal. But what the question is saying is, this normal intersects the graph at another point. What are the coordinates of the other point? That's what they're asking, right? What is that point where the graph is going to connect with this normal, which has an equation of y equals x minus 1? So what do we do? Right? Good. So what do we do now? So I'm just throwing it out to the class now. I have the equation of the normal. It's y equals x minus 1. How do I find where this is going to connect with the function? The function is the 1 over x minus 1. I want to know what are the coordinates where this thing intersects the graph at another point. What do you think, folks? How do I find that? Anybody give me some suggestions to that? And I'm just throwing it out to the whole class. I have the equation of the normal. What do I do? Where does this normal intersect with the graph? It intersects at one point already, which we already know, which is the 2, 1. 2, 1. Where else does it intersect? Where else does it intersect with this graph? Can anybody help me with that? Where else does it intersect with this function, I should say? How can you find where two functions intersect? Right? What's the strategy for that? I have set them equal. Thank you. Well, you could call it substitution. It's really just setting the two things equal to each other. So we're going to take the y equals x minus 1 and set it equal to the 1 over x minus 1. That's exactly what we're going to do. So the x minus 1 is equal to the 1 over x minus 1. All right, let me show you that again. Here's my original function. And I now have another function, another equation, x minus 1. That's the normal to the curve. I want to find where this normal intersects with the other line. Just set them equal to each other. Absolutely. And of course, we've done this cross multiplication before. So it's going to be x minus 1 times x minus 1 is equal to 1. Okay, so I'm really squaring x minus 1. So that's going to be x squared minus 2x plus 1 equals 0. Okay. Well, not 0. Sorry, that's rubbish. Is equal to 1. I don't know where 0 just came from out of the blue. Is equal to 1. So actually, it looks like we could just take that 1 from the two sides and we're left with this. X squared minus 2x, that's equal to 0. So how do we solve this? Right? It's a quadratic. How do we solve this quadratic? How do we solve any quadratic? We factor it. So I'm going to factor out the x. Okay. So what are the two values of x that come from this? There are two values of x that come from this. Two possible values of x. Thank you, Ashfan. 0 and 2. 0 and 2. Well, one of them, we already know, the point 2, 1. That's one point where it connects. The other point where it connects is when x is equal to 0. So what I'm going to do is I'm just going to plug 0 into the function, which is this function right here, and see what the y value is, because that's what I'm trying to figure out, is what are the coordinates of the point. We have one coordinate already, which is 2, 1. The other coordinate occurs when x is equal to 0. So I'm going to go ahead and plug 0 into the function. So it's going to be 1 over 0 minus 1. It's 1 over x minus, 1 over 0 minus 1, which is therefore equal to minus 1. So the other point is 0 minus 1. All right, so one point of connection for this normal is at 2, 1. The other point of connection is at 0 minus 1. There you go, done. Let's see if we can squeeze maybe one more question in. We went through these fairly quickly. I know I didn't finish some of the questions, but if you're not comfortable with any of them, you should let me know. All right, number 9. There's only one more after this. So let's see if we can do this. The concentration of drugs in a person's bloodstream modeled by this equation where time is in hours, or what interval of time is the concentration increasing? Well, we've never actually tackled this before, where we're talking about where something is increasing. We've talked about where the slope is horizontal, or a specific value of this. We've done that, but we never asked about where the function is increasing. One of the things that we do on the curve sketching unit is address exactly that, but we can talk about it right now. If I have a derivative of a function, we know it has to do with derivatives. If I have a derivative of the function, how would that derivative help me to figure out where the function is increasing? Can anybody give me a suggestion as to how the derivative might point me to where the function is increasing? Because it can show where the slope. Taj, nice, Adam, and nice, Taj, very nice. Wherever the slope is positive, a positive slope means the function is increasing. That's exactly right. That's exactly what the positive slope means. Because if the slope of the derivative is positive, the function is increasing. The function is going up. That's exactly right. So if we can figure out where this function, this derivative, I should say, is positive, the function itself is increasing. Taj and Adam are 100% correct. So let's see how much of that we can quickly do here. Let me see if I can derive this quickly. So we could do this as a quotient law. In fact, I'm going to use a quotient law to do it. So I'm going to say the derivative of the top is 24, and then multiply that by the underived bottom, x squared plus 2x plus 17 minus the derivative of the bottom, which is 2x plus 2 multiplied by the underived top rather, which is 24x plus 24. And all of that is over the bottom squared. X squared plus 2x plus 17 all squared. Because only show it. Okay, all right. So let's see how much of this we can squeeze in before the clock runs out on us. So this is gonna, did I do this right? Let me just double check. That's 2x plus 2 times 24x plus, yeah, okay. So 24x squared plus 48x plus, help me out, folks, 17 times 24. I have no idea. Can anybody quickly do that for me? 17 times 24. What is that? You all have the calculators hopefully close by. 228. Thank you. Minus, I'll put all of this in a bracket here, 48x squared plus 24x plus another 24x. So I'm going to say plus 48x. I'm not going to be able to finish this. You guessed it? What do you mean guessed it? Okay. So, okay. All right. You know what, folks? It's 238. 24 plus 48. I don't think we're going to be able to finish this. All right. I'll just put this other line here quickly. X squared plus 2x plus 17 squared. And of course, I'm now hearing I need to change this to 408. Thank you. All right. All right. Okay. We can go over time now. Daddy, you might be alone on that one. So I'm not even gonna chance it. I'm not even gonna chance it. Um, okay, let me just say this one thing, right? Because maybe some of you might want to try this on your own. When we look at the derivative of this function, after we do all of the stuff with no, no, really. We will have some time on Monday, just so you know, when we have the Monday morning class. When we do all of this stuff with the top and you tidy it up, we're going to be focusing on the top to figure out where this function is positive. And I'll tell you why. The bottom of this function can never be negative, right? Can anybody tell me why the bottom of this will never be negative? The bottom of this, when this derivative we're working out here, why is the bottom never going to be negative? Give me one quick statement to that answer, because it's squared. Thank you, Taj. So all we need to focus on, since it's a fraction, if the top of the fraction is positive, the bottom is positive, then the whole thing is positive. If the top of the fraction is negative and the bottom is positive, then the whole thing is negative. So when we come back and finish up this question on Monday, we're going to be focusing on where the top of the function is positive. Because you heard from Taj and from, I think it was Adam, and they said that as long as this function, as long as its derivative is positive, it means that the original function was increasing because it had a positive slope. And on that note, it's 2:40, and I appreciate those who would have gone past the time with me. But you know what, TGIF, it's Friday.